Okay, so this problem reads a particle moves along the x-axis from x equals 12.8 meters to x equals 23.7 meters under the influence of that force. Okay, so where the force F is in newtons and S is in meters, so find the work done by the force on the particle. So this is actually an example, a problem, so a chapter problem from survey. This is survey 7.56 problem. Okay, so let's make a new type script. And then okay, so let's say this as let's say example number 3. Survey 7. So this is a very simple application of integration because we remember that work done. Sorry. Work done is the integral of f d r from Ri to Rn. In our case here, the function is along x. So this equation can now be rewritten in terms of a simple product inside the integral where f, which is a function of x, and then dx. So remember that dr is dx x hat. And our f is f, so function of x hat, or I hat if you want. Okay, and our initial position will be xi, so this is your xi, and this is your xf. Okay, so this is the area under the curve of the f versus xf. Okay, so first thing that we need to do is to do the integration over this limits, and then we'll see the area under the curve. Okay, so let's do that. Okay, so let's clear the word first, and then let's define our variable. Our variable would be your, and then let's define the initial points, the initial station, and define. Okay. Let's define our formula. 375 divided by x cubed plus 3.75 times x. Okay, so let's see the result. So this is our function. Okay, so if you're going to divide 15 with 4, you will get 3.75. Okay, so let's try to show the graph. So it's our function f. So from negative 5 to 5, so remember that negative 5 to 5 is the example or the default range of values of x. So this function would look like this. Okay. So let's limit our plot within this region. So let's say we're going to limit the x-axis from 10 to 30. If you're going to graph that, it will look like this. So this is your graph. We're looking for 12.8 to 23.7. Now let's solve for the work. So basic work W is equal to the effect to X. Okay. Run this. It will look a very complicated solution. Okay. So remember that sometimes there are functions that are very, very difficult to solve. Okay. So let me expand this. So this is the solution. Okay, so imagine integrating this in your Math 147 or 146. It's really, really difficult. Okay, so MATLAB gives you a nice way to integrate such complicated functions. Okay. Now, of course, the work done should be integrated from this value to this value only. So we can do this by taking the same integral f, but within this limits, sorry, from x1 to x2, so that the value.
Sir, x2.
This should be x2. Okay, good, thank you. x2. Okay, so this is a very complicated expression. By default, the MATLAB gives you a fractional result. So we can convert the value to a double. And we can run again. So this is now approximately equal to, sorry, should be, okay, this is the value. Okay, that is about 0.8 meters per second. 0.8 joules of work. Now, as I mentioned, work is the area under the curve between these two limits. So let's try to do that shading. Okay. So what we can do is to actually rewrite, redraw our graph here by setting a numerical graph. So let's do our x-axis. Let's call this xx. Space between x1 and x2 with, let's say, 100 points. And then let's call the function and input all the values of x there. So what happens here is that when we define this array or this vector or this row vector, we will use that values and input it to our function here to produce these values. Okay? Just to give you an idea, I will give you, let's say, 10 values first, and then let's do some. So plot xx of ff, and let's say a circular black marker. Okay, so this is your function. Of course, we want this graph to be included in this graph. So what do? And then let's run it again. Okay, so these are the dots. Okay, of course, we want it to be as many as possible. So let's say 100. So this is 30. Okay, and we want to shade this. Of course, This is for demonstration purposes only. What's more important here, I'll demonstrate is the area function. So this area function is the area that will shade the area under the curve. So the syntax would be xx, and then that's right. Simple as that. This is the area under the curve. Then we can clean up this. Of course, we don't want this border, so we can uh, make the 9 style. Let's try that. Oh, sorry. It should be uh, colon. It should be colon. And okay. This is the area under. You can actually remove it by selecting none. And then the color, let's say base color, let's say green. Or you can make it gray. It can be done by defining a specific set of red, green, and blue values. So let's say for an RGB, black is 0, 0, 0 for RGB. For white, that's 1, 1, 1. So if we want a lighter gray, we must do some, we set this as close as 1, 1, 1. 0.9, 0.9, and 0.9. So that's fine. So that's your area under the curve. Of course, we can add this plot, but let's remove the markers and let's make it a line. Okay, so this is the area under the curve. Okay, that's it. Easy, right?